Hello everyone and welcome to a new stream. Today we're gonna keep studying for university. And wait, did I forget to change? Wait. What a great start! I forgot to change the. Oh, wait, let me log in here. Okay. Also, let me close this so we don't um, we don't use unnecessary RAM memory, right? So let me like my own stream and let me just edit this. So that's the fourth part, right? Uh, nice. Now everything works as it should, right? Okay, that's great. And what do we have right here? The fans are already spinning fast, so that's not a good thing. Can also remove this part since we already tested this. That was when we were developing our farm application, right? So what do we have right now? Now everything should be fine, right? Yes, that's the fourth part. On the last stream, for some reason, my brain just stopped thinking. I couldn't think. Like, I don't know what happened. Like, I was tired, yeah, but not that tired to suddenly stop be able to think. That was so weird. I don't know, I was kind of anxious. I don't know what happened. I I stopped to thinking, and now I think I'm doing fine right now. I slept. Uh, I think this should be okay. Also, what happened here? Okay, before we start, I wanna watch this video. What happened?
Stay inside, okay? Stay inside, okay? All right. All right. What's up, man? No, just going through a turn of the events.
Wait, what happened here?
I'll just go back to my shack, you know what I'm saying? Okay. That's it, right? That's all, man. That's it. Okay.
Did this what him?
Excuse me, miss. I didn't pay yet. I don't think I paid. Did I pay? I can't pay. Nigga. I don't got Apple Pay on this. Ain't got Apple Pay on this, nigga. Ain't no way I ain't see you in 4 years. And this is right. I'll be honest. 4 years later. Like, bro. Tell me something was new, bro. It's been 4 years. Had a girlfriend, got cheated on. Man, I don't know, like, locked in. Okay, we locked in. Finna get some shit going. Okay, man. I would love to work. Let's do a workout. Let's do a workout soon. Okay, all right. Hit the weights. All right. Crazy. Okay, I'm glad you're trying to better now. Okay. I am trying to better myself, man. That's why I had to come here to let you know that in person, man. I couldn't. This couldn't. This.
What the hell?
What the hell is going on? Why is there so many police at this KFC? Ain't no way. What the hell is going on? Yeah, I was just in there.
I think someone called the SWAT because you were someone spotted you, brother.
Oh my God. God bless America.
Yeah, I think that's what happened.
Oh shit.
You're telling you to slow down.
God, y'all scared me. I thought something was going on.
Sorry, dude.
It's all right. God damn. Yeah. False alarm. False alarm. Damn, who did that?
No, go stand up there on the sidewalk. I'm telling you to go stand up there on the sidewalk.
For what?
Go stand.
I'm not breaking any laws.
Yes, you are. I'm giving you a lawful order to stand on the sidewalk. Go stand on the sidewalk.
Stand on the sidewalk, bud.
Just stand on the sidewalk. Just stand on the sidewalk.
Go stand on the sidewalk. You're not interfering with the investigation. It's the law. You understand?
I didn't do anything.
What the hell is going on? Okay, let's just leave. Who the swatted me, bro? We leaving, bro. We out. We leaving. We leaving, bro. Somebody.
Hey, wait. Yo,
We out, bro. They got you detained.
Why you got the black guy detained?
Chill. Oh my God, bro. Y'all swatted us, dude.
Yo, that's
God,
not
man.
good.
See, Chad, this is the reason I don't do USA IRO streams. This is the reason why. I get swatted every time I do shit in America. Y'all play too much, bro. Y'all play too much. I keep doing that shit. That should be annoying, bro. Now I can't even leave.
Hey. Whatever you guys do, stay inside, okay? Stay inside, okay? All right.
What's up, man? No, I'm just going through a turn of events. I'm trying to, bro. I came here to get KFC, and I get swatted. I know, but I got swatted. I didn't do shit. That's the thing. Where you at?
What's up, man?
What's up, bro?
What's up, man? How you doing? Where'd they go? Uncle Wayne.
Free Unc, man.
You guys got when you guys were inside the
Yeah, but I got my uncle detained.
No, I get it. All I'm saying is, if you want, just show my stars real quick. You guys were in there and nothing was going on.
Yeah.
That would be super easy.
So who?
So you have it on the recording?
Yeah, it's right here. I'm live right now.
The reason why is because they gave us a description, which you know how it goes.
Petty, that's all it is.
Yeah. So that's all it is.
Who do I explain this to? You?
Come back over there. He's telling us to come over here. Can I see it?
I'm just a famous streamer. They just like, I'm a famous streamer. I was just at the KFC eating as normal. And my friend came in. He's a bit, that's him. And we were just eating. Just doing nothing. Nothing happened. Yeah, you see? See? Nothing happened. Nothing happened.
What's with the watermelon?
Nothing happened. Nothing happened to the point where 20 damn police cars came.
But you heard what came out.
Yeah, I know.
And so that's why we came like this.
What was the call was?
It was said that someone was on the counter, and they had a gun, and they're throwing out food and all this other stuff.
Okay, no.
So
No, I was on the counter, but nobody had a firearm
why were
or
you on the
anything.
counter?
Because the food was good.
So that's disrespectful to KFC,
No, I called the KFC before.
and they say you can go on
Yes,
the counter.
yes.
All right, whatever they want, then.
Come on, bro. I'm not just a random. Don't. I showed you right here. Like I said, like I said, it was a SWAT. I don't know what else you want me to show you.
Bro, they can't make us stand over here.
Why is he trying to make
Can't
a?
even detain Wayne.
Yeah, like why is he trying to make something out of nothing? Why were you on the counter? Like he just like, bro. I don't like how this cop just try to make nothing out of something. Like he's trying to find something to, I don't know, I don't know. You work at KFC?
Yes.
Can you tell these cops? Can you tell these cops to chill?
Can I take a picture?
Yo, bro, you work at KFC. You gotta tell them to chill. Nothing
I
happened
should
there.
speed. Could you just say shout out to Greg Pomo? He love you so much,
No,
bro.
no, you gotta
He love Ronaldo.
You have
Yeah, I
to.
just watching your screen. Like, yeah.
You have to help me. You work at KFC. Can you tell them that nothing happened in the store?
Yeah.
Then go.
But no, I'm just coming. I'm not. Yeah,
Buddy,
I'm
there's
coming
five.
right now.
There's 5 cops around. Can
I'm
you do
just
me a-
coming right now, but I don't know nothing, bro. I'm just coming. I'm not even clocking.
Oh, you wasn't cooking the chicken?
Yes. No,
Why
I'm
you got
just
a whole
coming.
KFC fit in?
Yeah, I was KFC employee, but I'm just coming right now. Could you just say shout out to Greg Pomo? I'm from in 80.
Shout out to Grand Pono.
Greg Pomo.
Grand Pomo.
Yeah, shout out to Greg Pomo.
What the hell? I do so
What
many
the
streams
fuck?
in so many countries, bro. Like, y'all be trolling so much. Can you only SWAT in America? Like, is that only a thing? You good? You good? We can go? Damn, bro. What the hell was that?
Wow, that's kind of I don't know, like wow. So now let's see how to calculate the inverse of a matrix, because I don't wanna follow this book step by step. Like I wanna try to like how I learned programming language. I didn't follow a book. I just searched online how to do things, and I wanna follow the same approach. And I wanna follow the same approach for linear algebra, right? So I don't wanna follow this book. Wait. Also, when I learned C, the fuck? Bro, what just happened? Okay, I'm back on the stream. Guys, I don't know what happened, but the stream got suspended for I don't know. I just got this email, right? So they suspended the stream because of copyright issues. But honestly, I don't know what happened exactly. Like, they didn't give any other info. Like, I'm back. It says that I'm... Jesus fucking Christ. I mean... Oh my god, don't... Oh god. Let me just... What the hell is going on? So... My stream got temporarily suspended for copyright notations. I don't know what happened exactly, but I I don't even use the music to earn something, but like if it is a problem, I can just remove the music. But I credit everything. I credit the music at the start, and I also credit on the music on I used on the intro, right? Like I don't know what happened. I never had a problem, but this time for some reason I had one. Probably because I watched another video. I don't know. I don't know. Like I don't I the restriction got removed. I don't know what happened, but you can clearly see that I was offline for a bit. Like, let me just put this. Oh my god! Don't do this. So as you can see, the stream was unavailable. Right? I actually never seen the screen. Like this is completely new for me. And then I got this email, right? Like they didn't tell me anything about it. Like they just told me that the stream got suspended for copyright. I don't know. I don't know. This happened while I was watching Aisha's Speed, that clip. But anyway, let's go back. So I was saying, if that didn't capture, that I wanna right now I wanna try to learn how to calculate the inverse of a matrix. Right? The multiplication gives us the identity matrix. That means for what I suffer from the video from 3b1b, the inverse of a matrix cancel out the transformation by another matrix, right? It's right. It's like I don't know. It's like multiplying a number by the inverse of another number, and that actually makes sense because it's like multiply this by this, right? And this gives us 1. So the same thing, the matrix, right? I'm gonna call this times this, right? Gives us I, right? And visually it cancels out the transformation. You can visually see it thanks to that linear algebra playlist. Also, why are fans spinning? Oh god, go away. There are no, go away. Microsoft compatibility telemetry. You are not that useful. So for those you don't know, also this notation can be represented as this, right? That's basically what it does. It makes sense. So the thing I was saying before is I'm not gonna follow this book, because this book, like, yeah, there is nothing wrong. It's actually a pretty good book, but like I learned C, I didn't learn following books. Like I didn't read any books. I just searched online how to do a certain thing, and this worked really well for me. So why it shouldn't work for linear algebra, right? So I think we should do this. We should try to hit the same approach for linear algebra, right? It worked for C. Why it shouldn't work for linear algebra, right? Or other things. So let's try this. Let's try this approach. So I'm not gonna follow this book in order, right? Because I wanna the last time I wanna find out how to calculate the inverse of a matrix, right? And to do this, we also need the Gaussian elimination. Then we have the augmented matrix, which I think this is like we concatenate the identity, right? Oh, that's why they introduced this row echelon form. That's probably why. So this multiplied by this should give 1. I mean the identity, not 1. I mean the identity matrix. So let's see how we can do this. So we have the reduced row echelon form, right? We have it right here. Let's search on YouTube how to perform these operations, right? So we have the row echelon form, right? What that is? Oh, I know what that is. Okay, I know the term in Italian, and that means riduzione a scala. Riduzione a scala di Gauss. That's the term used in Italian. In Italian, that's the Italian term. And yeah, that makes sense. So we should see how to do that. Let's simply search how inverse of a matrix, inverse matrix. Okay, that's really similar to this book, right? So we visually know what happens graphically, but now let's see how to do that using an algorithm, right? And let's try to wait, this isn't okay, this is the form builder. Let's try to put it right here. I mean, the last time we managed to create a function that calculates the determinants of a matrix, right? Okay, null space is also the kernel of the matrix, right? And that means that visually is the part that it's squished in a single point, right? I think I have to rewatch this video to understand it better. And let's see how to calculate this.
In this video, we're going to talk about how to determine the inverse of a 3x3 matrix. So let's say if we have matrix A, and it contains the elements 1, 2, negative 1, negative 2, 0, 1, 1, negative 1, and 0. So go ahead and determine the inverse of matrix A. So first, we need to rewrite this in the form of an augmented matrix with matrix A and the multiplicative identity of a 3x3 matrix.
Okay.
So here's matrix A. It's 1, 2, negative 1, and so forth. And the multiplicative identity matrix is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. So now here's what we need to do. We need to perform elementary row operations and basically take the left side and make it look like the right side. Now the operations that we apply to the left side, we have to apply to the right side. So the right side is going to change as a result. And whatever the result is on the right side, that is going to be the inverse of matrix A.
Okay. That makes...
So let's begin by turning this number into a 0. To do that, let's subtract row 1 by row 3. And let's apply the result.
Oh, that stands for row. Wait, hold on. Okay, we have this, right? Swap with row 3, and it actually swapped. Okay, that's pretty much how it works. Like, Jesus, it was that simple. So we definitely need a function to do that, right? Also, can we define? Also, let's also define something, right? So when we let's also define the null matrix, and this will just create a new matrix. Why am I? And then pass 0. And don't worry, nothing will be allocated in the memory. So this null matrix actually calls this function, and it returns a null matrix, right? Actually, do we also have null matrix? Are you fucking serious? This term actually exists. It's actually the matrix, and they all have 0. So we can call it null. Honestly, I don't even know how to call it, because this is actually not the matrix filled with zeros, but actually it's nothing. This is nothing. Like nothing is allocated. So when we create a matrix, it's automatically a null matrix. But this null matrix is different. I know there is some redundancy with these terms, but that's basically what it is, right? We can also just pass this, right? Can we? So we put 0, 0, and then null without calling the function. I will wrap this inside an expression just to probably that could work. Let's see what we get here. Let's try to bring that out. Just trying to test. So let's print matrix, and then we will print null matrix, just like this, just like that, right? And honestly, what notation should we use? Should we separate null and mat with an underscore? I'm not sure, honestly. I'll do that just for clarity. So we don't get an error. Let's try. And it compiles. Yeah. So we have we cannot print null matrix because it's not valid. Right? So to optimize this, if we return this, we can simply return null matrix. And this will be better because we don't even have to call the function. Right? That's a good thing. So I have this, right? So let's go back here. So we have an identity matrix, right? We can also define this. We can also retrieve the identity matrix. So but the thing is, we also need to make some moves to the matrix, right? We have to turn it into a row echelon form, right? So that's what we are going to do here in C. So should we get a new matrix? And just so let's add a new function and let's call this row each lone, right? Then we pass the matrix and this, right? Is this applied to only one matrix, or you know, we have multiple ones? Not sure, honestly. So we also have to pass, I don't know, let's pass another matrix, and we will pass probably so we pass a size D, a size T, or simply we'll pass an array of matrices, right? And I don't know how to call that matrix. Like when we I want to also pass this, right? So it can be transformed, right? Let's call this, I don't know, how should we call this matrix on the right hand side? Oh, augmented. So the augmented matrix is just appending the matrix onto. Okay. That's probably what. Yeah, that's what it is. I will just use this term, augments. That kind of makes sense. So this will affect all the matrices until it will encounter the null mat, which is the invalid matrix value. And so can I just, what if I delete this? Okay, I can pass this. I don't know what will happen. Nothing. Literally nothing happens. Wait, did it segfault? It didn't even segfold. It literally did nothing. Like nothing happened. I don't know. So if we want, we can delete the non-matrix and nothing will happen. That makes sense. So this matrix will return this matrix, right? Like this matrix transformed. These are just, you know, this part is just a pointer, so they're just here. Like they are just, I don't even know how to say it. But before we do anything else, let's create a new function that copies the matrix. So we have the matrix, and this will return another matrix with the same properties. And this is actually pretty easy to implement. So let's go here. Huh. That's interesting. So let's create a new matrix and let's call it copy matrix. Wait. We need the matrix like that, right? So the only thing we have to do is so we have this, so we create a new matrix, right? And we'll create the new matrix with X and then Y. Wait, I mean rows and columns. Then what we have to do is we have this, right? And this part, and this should be copy. Right? So out data, then we have the source, which is matrix.data. Then we have the size, and the size is we have matrix dot rows times matrix dot columns multiplied by size of every single cell, right? And then we will return the output. Right? That's what we are going to do. So what if I want to print the copy of G? Can we do that? Let's try that out. And yes, that's pretty much how it works. So we definitely need that. Also, we need to create a function that switches the rows and the columns. And this is an advantage. This is a big disadvantage if we use the single line of arrays to indicate the matrix. That's the only con I see when we, when you compute this type of operations, right? So we will return white. Then we have to switch rows, right? Then we take the matrix, then we get the size type of and we get row 1 for just X and then Y. The same thing applies to columns, right? So we also have to implement this function to make things work. So after we calculate the determinant, it is right here. Let's implement these two functions, and that will be really easy to do. Oh god. So what we need to do right now is we have to allocate memory, right? And this will be the buffer of the temporary memory, right? So let's create our buffer. And the buffer will be a mat set pointer buffer, right? And we should allocate matrix dot columns, right? Multiplied by sides of this. So what we are doing right now is we have to switch the rows, so the rows has the amount of columns elements, right? Then we we have to store the data in the buffer, right? So we have size t I equals to 0. Probably we should use this. Yeah. And do we actually need a buffer, or simply we can just use a single variable? Like, if we use a single variable, that would be much faster. The execution time would be improved. So we get matrix dot columns, right? Then I++. So let's create this variable, and this will be, I don't know, t, right? And let's try to store the value of the matrix. Then we have to store the I, which is the column, right? Like that. So to switch this, let's call this function, right? Then we have y, right? And then I, and we evaluate this, and we assign this. Actually, this should be right here, and this one should be right here, right? And finally, we just assign this to t, right? That's basically how it should work. So let's see if that actually works. Also, let's return the let's always return this. Should we do this? Should we return a pointer? Is it, or is it pointless? Haha. I think it's actually pointless, returning a pointer. So let's see. So if we have this matrix, right? So let's pass switch rows, then we pass f, and let's switch this, the second row with the 4 one. So we simply type 2 and 4, right? For some reason this, I forgot to specify this, right? Just like that. Here we go. Now let's see. Oh god, fucking damn it, what the hell? That's not good. Oh, I forgot to return matrix. Like, not a big thing, but you know. So let's do that, and here we are. It actually switched. That's cool. That's cool. It works. That means that it works, right? So for this, and we did the same exact thing. Actually, we should always check if x is less than 1 or y is less than 1. If it is, we will return this, right? Also, the same thing applies with the matrix, the rows and columns, right? Should we also check this? Don't know. Like it will return this because it doesn't. It won't even enter the loop. So yeah. So the same thing we should do right here, but this time we just switch this terms, right? Like that. Now let's try to switch the columns. Right? Let's do this. So we have second column and the third column, right? It's 3, 0, 4, 2, negative 1. So we get this, and look at this. It works. Wow. I think this is the most efficient way to do it. So now, when we have to switch the rows, we can just pass this, right? And that's basically what happens. So a new matrix, right? And we want to set the matrix from here. Like we can easily do it now. We don't have to call it separately, right? We can just do this, like this. Oh god, I'm just wait, hold on. I also forgot to adjust this. Here we are. And now we can print it directly. How cool is that? So we can do this in a single line of, just using this simple call. In one single line, we print the determinant that calculates the matrix which is set on this, right? That's cool, right? We can do this. And it prints the right result, right? We literally replace this. I will keep this. This is really convenient, right? We also have this approach, but I really don't like it. I really don't like this approach, honestly. Like, no. Because there are more operations and it's quite tricky also. So we have everything we need, probably. Can we also have augmented matrices? I'm not sure, honestly. I'm not sure if we should put the augmented matrix like this, because we can lose track of where we actually appended the other vector or matrix. So I don't really know. So let's keep going. Oh damn. So before we jump into this video, let's see how the best way to get this form, right? So we finally created the functions, so we can use these two functions to define the to get the row each transform, right? Also, let's specify this that doesn't allocate or no allocation, no memory allocation. We'll just specify this. What the fuck? Why is it? Okay. That's the same thing right here. So even if we return this, like no allocation will be, no new matrix will be created, right? So now that we have this part, oh, now we reach the Gaussian elimination, and I know this is really useful if we want to solve linear equations, right? We want to find the unknown values. So let's check the best way to do that, right? Also, is the right part involved or not? I don't know. Also, I will delete this just to make it clean, to make the code way cleaner. Also, probably I would also delete this. Like, we never had the we never had we never needed the use of the flags. So let's delete this for now. So this code looks really clean, and I like that. That's a good thing. And this was probably deprecated. Like, yeah, probably. So we will use set matrix and we will use the macro, right? We defined here. I like how things are start to have a shape. Like, we actually implemented so many functions, right? Like, I know they are basic functions, but it is something. So now let's see, let's check one of these videos. Let's check this one, this guy.
In this video, we're going to focus on using the Gaussian elimination to solve a system of equations with three variables. So let's...
Oh, there's also the Gaussian Jordan. And that's interesting.
Start with this problem. Let's say we have x plus y minus z is equal to -2, and
okay, this is
x minus y.
So in this case,
z,
he's using this method to
5,
solve linear equations.
Plus 2y plus 2z, and let's say that's equal to 1. So how can we use matrices to solve this system of equations? The first thing we need to do is convert it to an augmented matrix. So let's write the coefficients in this matrix. So we have 1x plus 1y minus 1z, and let's use a vertical bar to separate the left side from the right side of the equation. So I'm going to put -2 on this side.
Yeah, that's what we...
Now, for the second equation, the coefficients are 2, -1, and 1. Now, for the last equation, it's -1, 2, 2, and 1. Now, what I'm going to do is convert this matrix into row echelon form.
Okay, that's what
So
we have to do.
These three numbers to be 1, and I want these numbers to be 0.
Wait, I didn't know the part that we had to... Wait, wait. Okay, let's
But
keep
let's
going.
make those three numbers in blue 0 first. So what I'm going to do is I'm going to add row 1 and row 3 together. And I'm going to apply that change to row 3. So first let's rewrite the matrix. The first row is not going to change. All of the changes will be applied to row 3. So I can rewrite row 1. Row 2 is not going to change. Now, row 1 plus row 3. So for column 1, it's going to be 1 plus negative 1. And so that's going to be 0. And then it's 1 plus 2, which is 3. And then it's negative 1 plus 2, which is 1. And then it's going to be negative 2 plus 1, which is negative 1. Now the next thing I want to do is convert this 2 into a 0. So I'm going to apply the changes to row 2. I'm going to multiply row 1
So row 1 times 2, right?
by negative 2, because this will
Yeah.
become negative 2.
I mean,
And
negative
then
2,
add
yeah.
that to row 2. Some
Okay.
I'm going to write it out step by step for this one. So here's the operation that I'm applying. It's called a matrix row operation. So for column 1 and in row 1, we have an entry 1. So R1 is going to be 1. And for row 2, column 1, the entry is 2. So negative 2 plus 2 is 0. So this is going to be 0. Now for column 2, we're going to use these two numbers. So in column 2, R1 is 1 and R2 is negative 1. So this is going to give us negative 3. Now for column 3, R1 is negative 1 and R2 is 1. So negative 2 times negative 1 is 2, and then add 1 to that. That will give you 3. Now, for the fourth column, R1 is negative 2, and R2 is 5. Negative 2 times negative 2 is 4, plus 5, that's 9. Everything else will be the same, so let's rewrite the other numbers.
Should we keep track of the changes? So now we have to sum this, right? We just have to sum, to apply the last changes for this row and sum for this, right? Because 3 plus negative 3 is 0. So we have this part 0, right? Then we have to convert this into 1, right? Or something like this. Let's see if
And then
that's
let's
true.
get rid of this. So what do you think is the next thing that we should do at this point?
I already told this, and let's see if that's true.
Now, we need this number to be 0.
Yes.
So all we got to do is add rows 2 and 3. And we
Yes.
have to apply the changes
Okay.
in row 3. So it's going to be R2 plus R3.
Exactly. Yep.
So row 1s and row 2 will stay the same. So if we add R2 plus R3 from column 1, that's 0 plus 0, so that's equal to 0. And for column 2, R2 plus R3 is going to be negative 3 plus 3, which is 0, which is what we want. And then for column 3, it's 3 plus 1, which is going to be 4, And then for the fourth column, 9 plus negative 1 is 8.
Now do we have to convert that number in the center of the first matrix to 1?
Now, if I wanted to, I can convert this back to a system of linear equations and use back substitution to get x, y, and z in this form. But what I want to do is convert it to row echelon form. So I want to convert these three numbers into a 1.
Yeah,
I don't
that's what we
exchange
have to do. Honestly, when we do the row echelon form, we have to call the Gaussian elimination first, right? So what is the Gaussian elimination? It's actually what the hell? Bro, what the fuck? The page. Oh my god. Can you just don't do that? Holy shit. Oh my fucking god. It crashed again. Guys. Okay. I fucking hate. What the fuck is this? No. Oh my god. Fucking hate when this happens. Let's close some tabs. Oh god. Let's close this. Let's close this. Should we close this? Yeah, let's close this. Let's close this. Probably everything is good now. So let's reload the page and let's search for the Gauss elimination. We also have the Gauss-Jordan, which is the enhanced form, right, of the Gaussian elimination. But I'm gonna implement this. Right? So what we have here, we should have zeros, right? So we have to apply this method right here. Like before we call the row echelon, we apply the Gaussian elimination. So we get the matrix, right? Okay. And this will be useful to solve linear equations using matrices, right? And that's really interesting. So before we implement the row echelon, we have to get this. Also, let's pass matrix C augments. Here we are. And an augments is let me move this so we have everything aligned. So and let's say that augments is an array of matrices terminated by null mat, which is it's not a null matrix, but it's the matrix with nothing, literally nothing. So oh god, we also specified that here, right? So we have a clear documentation in the header file. That's good. That's cool. So let's make the Gaussian elimination, right? So we have this right here. So we have the, wait, let me just copy the signature of this function and paste it right here, right? So now what we have to do is we have to check if the amount of rows is equal to the amount of rows of this matrix, right? So let's do this. So we create a while loop. Then we have actually this should be a for loop as size t I equals to 0. Then we have arguments I will assign this to matrix type, and this time is a pointer. I don't care, this time is a pointer. And we'll call it A, like this, right? Actually this should be like that. I plus plus. Why it doesn't, wait, the fuck you mean expected? Wait, what? Wait, what? And this should be different than the matrix, right? Honestly, the fuck is he doing here? Let me just, can I just use this? The fuck, bro? Also, we should difference this. I don't know. I expected an expression, but we have this expression, right? Let me just declare this outside. This is matrix type, right? So do we have to do this separation right here? Don't understand what does that mean? Probably don't know. For some reason we still have an error right here. Fuck you mean? Oh my god. Don't understand why this should be allowed. Literally, what that means? This is a pointer. This is a pointer. This is a pointer. I don't understand why it doesn't consider it as a matrix type argument. Am I missing something? We should. Let me just. Don't know. Let me just do this. Don't know. Let me just. This is already pointer. Don't understand why it should work. Like I casted everything, but I still get this fucking type error. Let me just. No, this fucking thing throws an error. We have matrix type. Wait, I think we should wrap everything inside this thing, but we still have the. Wait. That's true. We should check. We should just check if. Okay, I know what's the problem. I know what's the fucking problem. We should just check if this is if data is null. We only have to check this. Can I just declare this inside here? No, we can't. We can't. What if I do this? No, we can't. We still cannot do that. Okay, that's okay. So now we have a pointer, right? So this should be null. So what if we take the columns, right? We should check if a dot rows is not equal to matrix dot rows, right? If they are not equal, we will return a null matrix. That's the check we have to. That's the check, right? So they must have the same amount of rows. And we already checked that, so we are cool. So now what we have to do is we have to start this. We have to start this type of, like, we have to make this thing work, right? Also, let's start implementing this. This function right here, right? And this we'll call this, right? So we have a new matrix, right? Then we have out probably, and we will call this and pass exactly the exact same arguments, right? Then if out so let's define a new macro. Wait, just need to do this. Okay, that's a cool tool. If this isn't valid, I will return null matrix. That's what we're going to do. Or else compute to do compute operations, and we will return the output like that. So the only difference between the Gaussian elimination and row echelon form is the output of the matrix. Like one returns a matrix with a triangular set of zeros, and the other one it still returns a triangle set of zeros, but it is delimited by a diagonal set of ones, right? That's the only difference that I noticed so far. Right? So let's try to watch the video about it. So we have so this is the Gaussian animation, right? And now let's see let's see a more mechanical way to do that. And I have an Italian video. I know I watched it before. It's an Italian YouTuber, and let's see what we get. What the hell? Why is speed? What the hell? Don't know. Wow, also this guy coded graphics. They use the metrics, but wait, why are you defining like met 4x4 identity? Ident equal. Don't know what do you mean by eq. Probably equals. But yeah, that's pretty much what we are doing here. Like you can simply pass the sides, right? Oh my god, am I still streaming? The fuck, bro? Let me just check if I'm still streaming. So, let me just. Bro, why is my internet so fucking bad right now? Oh my god. So, what we have right now is. So, you have the. Whatever that is. So, let's search this. Animazione del caos. This is an Italian video, right? And this shows how to do that properly. So, let's get into it. So this is a some-year-old video.
Essere utilizzato per risolvere agevolmente sistemi
Just
lineari. Per farlo, la cosa più semplice è considerare fin da subito un esempio e supponiamo quindi che ci venga chiesto di risolvere il sistema di 4 equazioni in 4 incognite che vedete rappresentato qui sulla sinistra. La prima cosa da fare, se vogliamo risolvere il sistema con l'algoritmo di Gauss, è costruirsi quella che si chiama la matrice completa associata al sistema lineare e che nel nostro esempio
In Italian is fucking different. The term is fucking different. It's matrice completa associata al sistema lineare. Wow.
esempio è quella che vedete rappresentata qui sulla destra. Come vedete, la matrice è costituita da due blocchi principali che vi ho colorato rispettivamente in verde e in azzurro e che si chiamano rispettivamente la matrice dei coefficienti e la colonna dei termini noti. La matrice dei coefficienti si chiama così perché i numeri che compaiono al suo interno sono proprio i coefficienti che compaiono davanti alle incognite nel sistema lineare. E quindi, giusto per capirci, l'1 che c'è qui è l'1 che ci ritroviamo nella matrice, il meno 1 che ci sarebbe davanti a questa y è questo meno 1 che ci ritroviamo qui, il 2 che c'è davanti a questa x è il 2 che ci ritroviamo qui e così via. E naturalmente quando manca un'incognita all'interno di una delle equazioni, come in questo caso la y nella seconda equazione, il coefficiente corrispondente che dobbiamo mettere nella matrice è 0. La colonna dei termini noti si chiama invece così perché i numeri che sono contenuti al suo interno sono proprio i termini noti delle equazioni del nostro sistema lineare. Cioè, per capirci, i numeri che compaiono a destra dell'uguale se, come si fa di solito, avete scritto il sistema in questa forma. In altre parole, quindi, la matrice completa associata al sistema lineare contiene tutte le informazioni fondamentali che c'erano nel sistema di partenza, ma ci consente di poter evitare di dover copiare ogni volta tutte le varie incognite e di doverci portare dietro questa colonna di uguali. Una volta che ci siamo quindi costruiti la matrice completa associata al sistema lineare, quello che vogliamo fare a questo punto è trasformare questa matrice in una nuova matrice che sia a scala. E per fare questo si usano sostanzialmente due mosse. La prima prevede, se necessario, di scambiare due righe tra di loro, mentre l'altra ci consente di sostituire ad una riga la somma tra quella riga lì e un opportuno multiplo di un'altra riga, cioè un'altra riga moltiplicata per un'opportuna costante.
Yeah, okay. The thing that he explained is that there are two ways to get the Gaussian elimination, and we have the first way, like we have to apply both ways, of course. The if we need to, I mean, the first way is to probably switch rows, and the other one is, I don't even remember, sum it together and multiply them. Yeah, probably not.
Nel nostro esempio, per trasformare questa matrice in una nuova matrice che sia a scala, dobbiamo innanzitutto far comparire degli zeri al di sotto di quest'uno qui, che sarà il nostro pivot della prima riga. Per farlo dobbiamo naturalmente liberarci di questo 2 e di questo 3. E come possiamo fare a fare questo? Beh, vedete, per far sparire questo 2 possiamo sostituire alla seconda riga la differenza tra la seconda riga e il doppio della prima riga.
Oh my fucking god, this is... Okay. So we have this, right? We have R2, and this is R2 minus 2R1. Yeah, that's basically how to...
In questo modo otterremo un 2 meno il doppio di 1 che fa 0. E similmente, per neutralizzare questo 3, possiamo sostituire alla quarta riga la differenza tra la quarta riga e il triplo della prima riga. Così in questo modo avremo un 3 meno il triplo di 1 che fa 0, poi otteniamo un meno 3 meno il triplo di meno 1 che fa 0 anche lui, un meno 2 meno il triplo di meno 1 che fa 1 e così via per gli altri due termini. Ecco, se facciamo questa coppia di mosse contemporaneamente, la nostra matrice di partenza si trasforma in questa matrice qui che, come vedete, comincia ad avere l'aspetto a scala. A questo punto la seconda mossa che dobbiamo fare è far comparire al di sotto di questo 2, cioè qui sotto, due zeri. Come vedete, il termine nella quarta riga per un colpo di fortuna è già 0, quindi qui non dobbiamo fare niente. Si tratta a questo punto di far sparire questo -1 utilizzando per farlo il pivot della seconda riga. Quello che quindi ci conviene fare è sostituire alla terza riga la somma tra la terza riga e metà della seconda riga, perché in questo modo avremo un -1 più metà di 2 che fa comparire lo 0 che cercavamo, e poi abbiamo un -2 più metà di 4 che fa 0, uno 0 più metà di -2 che fa -1 e infine un -8 più metà di 8 che fa -4. Arrivati a questo punto, l'ultima cosa che dobbiamo fare è far comparire uno
The fuck?
0 qui sotto, e per fare questa operazione di solito si utilizza l'elemento sopra di lui, cioè l'eventuale pivot della terza riga, in modo da fare una opportuna combinazione tra le righe e far comparire lo 0 qui sotto. Vedete che però stavolta il fatto che qui ci sia uno 0 ci impedisce di fare delle mosse simili a quelle che abbiamo fatto nel passaggio 1 e nel passaggio 2. E quindi come facciamo a cavarcela? Beh, in realtà le cose sono più semplici di come erano nei casi precedenti, perché vedete, se scambiamo tra di loro la terza e la quarta riga, cioè queste due righe qui tra di loro, otteniamo direttamente la matrice a scala che stavamo cercando. E quindi capite, siamo arrivati esattamente dove volevamo arrivare. A questo punto quello che dobbiamo fare è ripristinare le incognite, cioè recuperare quelle incognite che avevamo provvisoriamente messo da parte, trasformando il sistema di partenza nella corrispondente matrice completa. Ricordandoci a questo punto che la quarta colonna era quella che conteneva i coefficienti dell'incognita W, che la terza colonna era quella corrispondente all'incognita Z, che la seconda colonna era quella con i coefficienti dell'incognita Y e che alla prima colonna corrispondevano i coefficienti dell'incognita X, partendo dal basso questo -1 e questo -4 diventano per noi un -W uguale -4. Questo
Ok.
117 che ci ritroviamo qui, una volta recuperate le incognite, diventa uno Z più W uguale a 7. Questo 2, 4 meno 2, 8 diventa un 2y più 4z meno 2w uguale ad 8. E infine la prima riga, nel momento in cui torniamo in forma di sistema e recuperiamo quindi le incognite, diventa x meno y meno z più w uguale a 0. A questo punto abbiamo praticamente finito e per vincere non ci resta che risolvere questo nuovo sistema che abbiamo ottenuto e che però è fulmineo, cioè è facilissimo rispetto a quello di partenza. Perché? Perché vedete, dalla prima equazione si ricava immediatamente che W deve essere uguale a 4. A questo punto, se sostituiamo al posto di W il 4 che abbiamo appena trovato, dalla seconda equazione si conclude immediatamente che Z a questo punto deve essere 3. Una volta noti W e Z, se li sostituiamo nella terza equazione, si ricava facilmente che Y deve essere uguale a 2, e a questo punto noti W, Z ed Y, se li sostituiamo nella quarta equazione, si conclude facilmente che X deve essere uguale ad 1. Dunque possiamo concludere che la soluzione del nostro sistema sarà X uguale ad 1, Y uguale a 2, Z uguale a 3 e W uguale a 4. E naturalmente, per verificare se la soluzione è corretta o meno, è volendo sufficiente sostituire i valori che abbiamo appena trovato all'interno di queste equazioni e verificare se le cose tornano oppure no. Volendo quindi ricapitolare la procedura per risolvere un sistema come questo con l'algoritmo di Gauss, la prima cosa che dobbiamo fare è costruirci la matrice completa associata al sistema. Dopodiché, sfruttando le operazioni di cui parlavamo prima, si trasforma questa matrice in una matrice che sia a scala e a questo punto, per vincere, si ripristinano le incognite. Il nuovo sistema che si ottiene da questa procedura ha le stesse soluzioni del sistema di partenza ed è però di immediata risoluzione. Appurato questo, prima di salutarci vale però la pena di riflettere su quello che può succedere nel momento in cui otteniamo la nostra matrice a scala.
Okay, so to do that, we actually have to iterate for each column, right? I think so. So if we have a 0 and we don't have it at the bottom, we have to try that by yourself first before writing the algorithm, right? So let's suppose we have let's get rid of the, let's just do it for a simple matrix like this, right? We have this. Now I need some random numbers actually. I don't know, let me just what does that mean? Free division Gauss and free fraction Gauss? What the hell is this? There is no difference in the output, but that's the method attributes. Not sure honestly, but that's okay. So wait, how long am I streaming? 2 hours, okay. So what we have right now, I'm not sure. So what if we have 0, 1, 3, 2, then we have 1, 3, 2, 3, then we have 0, 0, 1, 3, and then we have -1, 3, 2, 3. Okay, I'm not that creative, but I want to know what should I do right now. Okay, the first thing is I should probably do this thing, right? We have this 0. Jesus fucking Christ. 3, 2, 3, right? Now we have the third column, 1 and 3, and this is where we should actually multiply this by, we should take this number, which is the pivot, right? And multiply it and sum it by, wait, we should multiply this, wait, let me just keep track of what I'm doing here. So we get the fourth row plus the third row multiplied by -2. So the first one are 0. Then we also have a 0, and then we have -6 right here. So it's actually pretty easy, right? Yeah. So this is scaled. This is the scaled. This is the Gaussian elimination applied right here. Let's keep track of these two terms, right? So if we have a 0, right? We should check if if we have if the bottom if the number at the bottom is also 0, or else we will switch the rows, right? So yeah, we should do that. So we definitely need a nested for loop. Actually, you should get from here. Then for each column, probably matrix columns, right? And then I++. I'm gonna try to think what would be the best way to do it. Using the C algorithm. Also, let's remove this. And probably should also remove this. We don't need it anymore. I'm just gonna delete some unused code. So we have something clean, right? So what we have to do right now, we have to perform this check, right? That's probably what we need to do. Like if we have a 0 and the bottom number is not 0, we should just, switch the elements, right? So we have another type matrix.columns G++. Like that. Actually, this should be applied for the rows. So if we have this, right? We have this matrix I and J is equal to 0, right? We have to switch the rows, right? Oh god. Switch rows. We have the matrix. Oh wait, hold on. We also have to check if the next row is not 0. So we just put that like that, right? If it's not, I will switch the rows I and I plus 1. Right? That is what we have to do first. Also, we should check if before we do that, let's check if I is less than matrix dot rows to avoid illegal memory operations, right? So after we switch this, right? How do we have it to do? Not sure, honestly. So the first thing is, the first step we switch this, right? And now we have this form, right? Not sure. Then probably will break. It will break, right? We will break the loop after we switch the rows. Also, actually, we should copy this value. Wait, let me just... Does this allocate memory? I think so. Yes, it allocates memory because there is no comment here. Like there is a comment, but there is no malloc sign. So let's create a matrix that will be the output, and we will copy this matrix, right? From here. Should we actually do this? I don't know. I feel like we shouldn't even allocate memory anywhere. Like we should, if we want to pass a copy, we will pass a copy explicitly, right? Not sure if we should actually do this or not. For now, I'll just return copies. But I will probably remove this, because I think that would be better. Like it would be much more flexible. If we want to pass a copy, we'll just wrap this inside copy. Should we actually convert this? I don't know, honestly. So, what if? Okay, actually no. Let's change this. No allocation will occur because this is a basic operation, right? These are basic operations. And the same thing applies here. Probably. So we won't even return the result. Right? So we won't even create a new matrix. We won't do that. We will just, for now, we will just assign it to X. Because that could be useless. If we want to pass a copy, we just specify copy. Right? So the scale doesn't actually allocate, but multiply and add, or probably sum. I think the correct term would be sum. Let's change this to sum. We didn't even sum right here, but we'll change this. Where is it? Here it is. Right there. Actually, this doesn't return anything, so I'll just remove this. So no malloc, I mean for those that return the matrix type. So no memory allocation, right? Fuck. Wait. Wait, what? Wait. What did I just saw? Like, I checked my phone and now, wait. If we go here, that's fucking insane. Holy crap. Ceylon is now free? What? Are you serious? Oh my god. Don't crash, please. Oh my fucking god. Oh god. So let me just close these tabs. If we go here, it's fucking free. No way. There is also the Rust plugin. Bro, that's fucking cool. This is... Wow. I actually have Sea Lion. Oh my god. Guys, it just crashed again. My browser fucking crashed. Oh my fucking god. I have it right here. And this is actually... my university has a license for the students, for us, and I'm using this license. But that's cool. That's cool. MSC string, because I think glitch out. That's fucking cool. So we have to perform these operations, right? And then we have to check individual rows, right? So if we check this, we shouldn't do this check. Actually, we shouldn't do this. So for each side, I mean for each rows, we will just do this check, and then we should also do this, like we should also iterate this for each individual elements like this. And yeah, we should do that. So we have k plus k, like that. And we also have to switch the rows for A and then Y and J, right? And this shouldn't allocate memory, so we will just, avoid this, right? So actually this, we can also do this. Wait, no. Wait. No. Let's assign this, because this can also return a null value. If a null matrix is returned, this is unchanged. This will be unchanged. So right now let's implement this. And let's see if that works. So the first two elements should be sorted, right? We don't know that. Let's try it. Let's hope that everything works. So let's go here. Actually, should we just get rid of all of this? Yeah, let's do that. Let's get rid of all of, because we already know how to calculate the determinant of a matrix. Now let's go here. Let's create a new matrix, right? Create matrix, and this will be a 4x4 matrix, right? Now let's print. Actually, we should print matrix, right? The Gaussian elimination of this matrix. So set matrix of A, and then here we pass a null matrix, right? Then we have to pass the values like that. What the fuck? This should be probably we should pass an array of matrices, right? Oh my fucking god. For some reason we can pass this. I don't know. Why can't we just pass? What the fuck? Wait. How does that work? Why cannot pass this? Let me just check this. What the hell? This doesn't make any sense. Should we pass the pointer? The address? No. I don't fucking know why. We have to pass an array, like we did it. Let me just pass this. I know it's... I don't know if... Like, I know they aren't the same thing. But let me try to pass this as this type, right? Now, what happened if I pass this? This operation is not allowed. The hell? For some reason I cannot pass this. I cannot do that. Trying to understand what's the fucking issue with that. Like, I cannot pass, I cannot, initialize struct. I didn't know that. We should probably use you know what, we should probably use this method right here. Yeah, I think this is the right way to do that. Jesus, I wanted to avoid variadic functions, but I guess I'm kind of forced to do. Jesus, I have to change everything. No, I don't think this would be a good idea. Can we just create this? We cannot initialize. This fucking sucks, honestly. This fucking sucks. Why is C doing this? Like, holy fuck. This could be avoided, right? So let's create a matrix type, no matrix, and we will just assign it to this value right here, and then we can technically pass this, right? We cannot? What? Wait, what the fuck you mean? We are not even initializing it. It's fucking stupid. We cannot fucking pass an array, what the hell? Oh wait, I'm fucking dumb. I'm dumb as shit. Oh my fucking god. Wait. Wait. I didn't. So this should be like that. Now it works. Now it works. Okay, that was dumb. Okay. So we pass a null matrix, right? So we have a matrix array. Then we have to pass. Let's try to pass this matrix. So we have 0 and 1, 3, 2. Then we have 1, 3, 2, and 3. Then we have 0, 0, 1 and 3. Then we have -1, -1, 3, 2, 2, 3. And let's see if that works. Not sure, but let's check this. And no, it doesn't. I probably know why. Yeah, exactly. I forgot to return. Wait, no, I need this. Let's try again. What the fuck? Wait, what? Why do we have... This doesn't work at all. Like, this shit doesn't even work. Like, why do we have... Why do we have a row filled all of zeros? At least the first one switched correctly, but for some reason we have this row. I probably know why. I probably know why. The problem is here. Well, I don't understand. Oh wait, I actually know what's the... So let's do this and let's perform this additional check, but I don't find it necessary, but let's try again, I guess. Also, I forgot to do this move. What the hell? Also, why did I put J here? It's I. We got... Wait. This isn't field of... Oh god. Let me just... So this one didn't switch. Wait. The things that we changed is this, right? We changed this. So we remove that, right? Then we apply this. What the fuck? No. And this actually... What the fuck? What the hell? What the fuck is going on? Why does this print zeros? This shit only prints zeros. You're fucking stupid. Well, if we remove this condition, right? Let's try to remove it. And now we have the other values. Oh, I know why. Because we are reading illegal memory pro. Yeah. I don't know why. Like the last term should be sorted, right? But it is not. Also, why are we? Hmm. This is way harder than I thought. I'm gonna take a short break. I'll see you later. Okay guys, I'm back. Took a break. So what do we do right now? So to try to understand the actual this thing step by step, we should compute this step by step, right? We should check the first column. So what we have to do, we should check if R2 is supposed to switch with R2, right? That's the question I'm asking. So let me check if it's still streaming. Okay. So that's what I'm asking. Should we switch this? And in this case, we should switch this. So we have to switch this, right? Now we can proceed. So we switch this to elements, right? So now we can proceed if we should switch this, the R2 with this. Should we switch this? So the new matrix would be, let me just draw this. So we have 1, 3, 2, 3. Then we have 0. Then we have 1, 3, and 2. Now we have 0, 0, 1, 3. And still we have this right there. So now we should check if this should switch with this. And this is affirmative. We should switch this. Right? So what we have to do is, we have this new matrix, right? We have 1, 3, 2, 3, and we have where the fuck does this come from? 0, 1, 3, and 2. Then we have 0, then again 0, right? No, wait, no. Wait, no, I got confused. We shouldn't actually switch this. So it will remain, it remains the same. So let's put that here. We don't switch this time because there is a 0 right here. Right? I don't know why it doesn't work. Also, we should get if we let's create a new variable. It's and let's set it to 1. So if row 0 is true, we have to perform these checks, right? Now if I have of the matrix I and j is not 0, right? We'll set this to false. Right? But what if Jesus Christ? But what if, like, we have let's try to run this. I know nothing will change, but let's try it anyway. I don't understand why, like, it should change, right? Wait. Actually, there was an unnecessary switch right here. There was an unnecessary switch. Actually, this isn't correct. Let me just try to do this. Yeah, I think this will be correct. And we get a different result. it's unchanged. Wait, no, it isn't actually. So what we are doing right now is we are checking if the next rows are zeros, right? So if they are all zero, and we get this, this should be equal to 0, right? Then we should wait. Wait, that's probably the issue. I don't know. The fuck? Wait, let me change this to let me just change this back to this thing, right? So we have to check the first column, right? We have to set if they are all zeros, right? And if we get this is a 0, so rows 0 should be true, and we get, and this is not equal to 0, we should switch, right? And that's what happens here. But this doesn't happen for the next column. Also, I mean, wait, it actually happens, but this shouldn't happen. So let me just print everything. I know this isn't a good idea, but let me just try that. So what do we have? So we have the first, wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Wait, let me keep track of I and J. Let's try again. So what do we have? So on the first side, we already switched this because it's on the first place. So we have this matrix, right? So this should be the result. Okay. The switch doesn't happen here. But it happens here. So we have the third row, right? That's weird. So we are performing this check and we are checking if I plus 1. Okay, we are checking I plus 1. Let's also print. Let's also print the switch, right? Maybe like this. And let's try again. And let's see what we get. So this one is switched. Then we have another switch on the third row. In the third row. And the third row it is like this. Wait, what? Why is this? Wait, this doesn't make any sense. So we check if the current row is 0 and the next one is, oh wait. Wait, it's actually true. Wait a minute. The condition is true actually. Wait. What's the right condition then? The rows at the bottom. Okay, I know what's going on. I clearly know. Also, let me just put this. So the thing is, it's actually checking if this one should be switched, right? And the third row, this is actually true because damn, that's the fucking reason. That's the actual fucking reason. That's why. Holy fuck. So right now I'm checking if this one is not 0, so it isn't. But then and checking if the other one is 0, but this. So we should keep track of we should also keep track of the next column, right? And actually, yeah, you should also rewrite the condition. So we get if this is applied and this is not equal to 0, and next, and then next, and this, yeah, we should also check if the elements are all 0 in the next line. And the fuck? I know why. Because it's just checking the next column. Actually, nothing is happening. There was no switch here. Probably should check this after. Let's try again. Fuck. Fuck. Wait, let me just do this. This shit still doesn't work. Fucking piece of shit. So we have a switch, right? This fucking sucks, honestly. Don't even know what to say. Actually, it should be different. Don't know, I'm not sure what I'm doing. I'm trying to what the fuck is wrong? There was no switch. Wait. It shouldn't be true. Let me try to check this. Ah, fuck you. Stupid fucking dumb bitch. Stupid fucking piece of shit. Stupid fucking hassle. So what if we don't apply anything? We get this result. But this fucking bitch shouldn't switch. But it does. And that's actually... And I know why. I know why this fucking happens. Wait. Isn't it supposed to happen? Wait, I think this is supposed to happen, right? Probably. Let's rewatch the video. Then we have to immediately apply the multiplication. Okay. You still have to keep track of this. Right? Yeah. Now what we need to do. We also have to perform these operations instantly. So let's do that. Just check. I'm streaming for almost 4 hours, but still trying to find a solution for that. So the first row is unchanged, right? So we can move. We have to rewrite everything actually. Trying to understand what's the best approach. Don't know. I don't know. Still trying to figure out. So let me just rename this to math set. Yeah, I think this will be better. So following this logic, we could also switch this too, right? For some reason this doesn't happen. Wait. We should check if I don't know. We should first compute the calculation and then switch, right? Trying to understand what's the wait. Let's try to compute the results, right? I'm not sure, but I quite understand how it works. So I will implement the Gaussian elimination the next time. Yeah, that's basically it. Like, you have the Gaussian elimination, right? It's actually pretty easy. I'll implement this the next time. For now, I'm just trying to understand how everything works. Like, I tried. Honestly, yeah, that looks more complicated than I thought. This is like we have to like it looks like there are some arbitrary operations that occurs in this process because we switch the second column with the fourth column, and then we switch the third column with the sec with actually we only switch the third with the fourth, but then we make this wait wait no, okay, they aren't that arbitrary. So let me just Wait, let me just. Okay, so what we have to do right now? I think we have to compute the operation first, and then we have to switch, or it just depends. So how do we know if we have to compute the operations or switch, or do both? I'm just gonna attempt to get the row echelon form. Okay, I looked on the. Okay, so wait. If we go here, I mean, if we search Gaussian elimination, we also have a GIF, right? That's the that's the that's the GIF we have, and there is an animation that actually explain it very clearly, right? So we have this GIF, and look at this. And we swap the everything, and we have it right here. So this is the process. So let's download this GIF. So we have this GIF, right? I cannot even post this GIF. Oh my fucking god. Why does the media viewer lack of features? So we have, let me just, okay, let me just try to open this with, I don't know. I don't even have, are you serious? I don't even have a VLC. Do we have this? Holy shit, what the I don't think this is clear enough. So let me try to follow this animation, right? I cannot pause, there is no way. So we have this. So we okay. Wait. This is way simpler than I thought. How do we have to multiply by 1? That's probably because we have the pivot. Okay. Let me just check again. So we always multiply by 2 because we have the pivot, which is 2, right? So I will implement this the next time. What is L? Oh, it's the I also have a pseudocode of this. A pseudocode. That will be useful. let's try to keep going with this video. So we just applied the Gaussian elimination. Now we have to turn it into row H4, right?
This is already 1, but these two, they need to be converted into a 1. So therefore, simultaneously,
so we should simply divide it, right?
For row 2, I'm going to multiply by negative 1/3 R2.
Yeah,
And
basically
for row
divide
3,
it.
I'm going to multiply by 1/4. So row 1 will not change. So let's rewrite that. And row 2, we're going to multiply everything by negative 1/3, or divide everything by negative 3. So negative 3 divided by negative 3, or negative 3 times negative 1/3, that's positive 1. 3 times negative 1/3 is negative 1, and 9 times negative 1/3 is negative 3. Now, 4 times 1/4 is 1, and 8 times 1/4 is 2. So now what we need to do is convert this back into a system of linear equations. So column 1 is the coefficients for x, this is for y, and z. So the first equation is x plus 1y minus 1z is equal to 2. For the second one is 1y minus 1z is equal to negative 3. And the last one is 1x is equal to 2. So in this form, we automatically get the solution for x.
Yep.
Now, it shouldn't be x, it should be z, because this is the column for z. So we should have that z is equal to 2 and not x. So we have that x solution for x. Now, it shouldn't be x, it should be z, because this is the column for z.
You made the mistake.
So we should have that z is equal to 2 and not x.
And that's
so
automatic.
We have the solution for z. And one other thing I missed, this is negative 2. I forgot to transfer the sign here, so that should be negative 2 as well. So now that we have z, let's plug it into the second equation to get y.
It's so annoying when this happens.
So y minus z, or y minus 2, is equal to negative 3. Now let's add 2 to both sides. So negative 3 plus 2 is negative 1. Therefore, y is equal to negative 1. Now let's take y and z, and let's plug it into the first equation. So we're going to have x plus y, where y is negative 1, minus z, and z is 2. That's equal to negative 2. So negative 1 minus 2 is negative 3. And if we add 3 to both sides, negative 2 plus 3 is 1. So x is equal to 1. Now we have the final answer. So in the form of x, y, z, it's going to be 1, negative 1, comma 2. So this is the solution.
That's cool.
And keep this in mind. This form is row echelon form.
Yep, row echelon.
You have a diagonal of 1s and 0s beneath it. It really doesn't matter what's here. So keep that in mind. So that's the row echelon form.
That's cool. That's pretty cool. Now, after we implemented these two functions, we should be able to solve linear equations, right? That's cool. So we simply learned so we now know what this does. I don't know why the swap occurs here, but as you can see, this is the Gaussian elimination. It didn't mention before. Yeah, that's what it does. Is in a convenient form the row each one from form ref. Reverting this compact notation back into the expression notation with the variables, we will obtain the solution. Particular solution is this. Then we have the general solution. And this is the set of all possible solutions. Still don't know what that is exactly, but yeah. So we have the definition of pivot, right? This is important. The leading coefficient of a row first non-zero number from the left. Okay, that's interesting. It's called the pivot, and it is always strictly to the right of the pivot of the row above it. That's true, yeah. Therefore, an equation system is in row echelon form. It always has a circuit structure. Yeah. You can see it right here. The pivots here are bold. And that's basically what it is. Then we have the -1 trick. So we can probably... Oh, that's cool. We can use this trick to fill the space, right? We will use this -1 trick. We will increase the size of the matrix, and we will fill it, and we will fill the diagonal with -1 where the one is missing, right? And then we can calculate the inverse matrix by Gaussian elimination. So we have the augmented matrix, and this will be with the identity, right? So let's go back here, and let's try to...
In this video, we're going to talk about how to determine the inverse of a 3x3 matrix.
To find this.
So let's say if we have matrix A, and it contains the elements 1, 2, -1, -2, 0, 1, 1, -1, and 0. So go ahead and determine the inverse of matrix A. So first, we need to rewrite this in the form of an augmented matrix with matrix A and the multiplicative identity of a 3x3 matrix. So here's matrix A. It's 1, to -1, and so forth. And the multiplicative identity matrix is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. So now here's what we need to do. We need to perform elementary row operations and basically take the left side and make it look like the right side. Now the operations that we apply to the left side, we have to apply to the right side. So the right side is going to change as a result. And whatever the result is on the right side, that is going to be the inverse of matrix A. So let's begin by turning this number into a 0. To do that, let's subtract row 1 by row 3, and let's apply the result to row 3.
Yeah, these operations are pretty arbitrary, but this animation will help me a lot. So we are subtracting to, yeah, because it is more convenient. They have the same number here. These two are equal.
Now, row 1 is not going to change. So let's rewrite that. Row 2 is also not going to change as well. Now for row 3, it's going to be 1 minus 1, so that's 0. And then it's 2 minus -1, or 2 plus 1, which is 3. And then we're going to have -1 minus 0, so that's -1. And then 1 minus 0 is 1. 0 minus 0 is 0. And then 0 minus 1 is -1. So now, what do you think we need to do next?
Okay, we have two ways. Like, we can switch the two rows, or we can, and then we can multiply this by the other row, right? I mean, we have to add this row with another subtraction, like with another row, I mean, and then we have to switch.
How can we turn this -2 into a 0? What row operations do we need to apply to row 2 to do so?
Probably -2 times -2 plus 2 plus, so we have plus 2 R1, right? I don't know.
So we're going to say 2 times R1
Yeah.
plus R2. Let's do that.
Yes. Wow. Sorry.
So we're changing row 2. Row 1 is going to stay the same. Row 3 will remain the same as well. So 2 times 1 plus -2, that's going to be 0. 2 times 2 plus 0, that's going to be 4. 2 times -1, which is -2 plus 1, that's -1. 2 times 1 plus 0 is going to be 2. 2 times 0 plus 1, that's 1. 2 times 0 plus 0 is 0. Now, let's turn that number into a 0. So, we need to apply the row operation to row 3. I'm going to multiply R2 by 3 because 3 times 4 is 12. And then I'm going to subtract it by 4 times R3 because -4 times 3 is -12. And they'll cancel to 0. So row 1 is going to stay the same, and let's rewrite row 2. So we're going to have 3 times 0 minus 4 times 0, which is 0. And then 3 times 4 minus 4 times 3, that's going to be 0 as well. And then 3 times negative 1, which is negative 3, minus 4 times negative 1, so we have negative 3 plus 4. That's going to equal to 1. And then 3 times 2 is 6, minus 4 times 1, so 6 minus 4 is 2. 3 times 1 minus 4 times 0, that's 3. And 3 times 0 minus 4 times negative 1 is 4. Now what we need to do is turn this number into a 0. So that's going to be straightforward. We just got to add
Wait. Huh?
row 1 and row 3 to accomplish that.
Oh, we have to turn this into an identity matrix, right?
So let's rewrite rows 2 and 3. So it's going to be 1 plus 0, which is 1. And then 2 plus 0, that's 2. Negative 1 plus 1 is 0. And then
Not
1
sure.
plus 2 is 3. And then 0 plus 3 is 3. And 0 plus 4 is 4. Now let's focus on that number. What row operations do we need to apply to row 2 in order to make it 0?
We can add it with the third row, right? I guess
All we
okay.
need to do here now is add row 2 and row 3.
Yes.
So notice what's going to happen. So let's rewrite row 1. And let's rewrite row 3. So row 2 plus row 3.
Wait. Wait, huh? What?
3. 0 plus 0 is 0. And then 4 plus 0 is 4. Negative 1 plus 1, that's going to be 0. And then we have 2 plus 2, which is 4. And 1 plus 3, that's 4. And then 0 plus 4 is also 4. Now, what we need to do at this point... Wait, hold on. I didn't copy this correctly.
Yeah, exactly. I think you were supposed to operate in this, right?
This is supposed to be 1, 2, 0,
Yeah.
and 3, 3, 4.
Yeah, that was why I was confused.
So everything else should be fine at this point.
Yes.
This is what I should have right now. So at this point, we need to turn this number into a 0. So we need to apply the operation to row 1. So let's take 2 times R1 and subtract it by R2. So we're going to have 0, 0, 1, 2, 3, 4, and then 0, 4, 0, 4, 4, 4. Now we're going to take 2 times 1 minus 0, so that's going to stay 1. And then 2 times 2 minus 4, that is now 0. 2 times 0 minus 0 is 0. And then 2 times 3, which is 6, minus 4, that's 2. The next one's going to be the same. 2 times 4 is 8, minus 4 is 4. And one thing I do need to fix, 2 times 1 minus 0, that's supposed to be 2. And I have a 1 here, so let's fix that. Now, what we need to do is multiply the first row by 1/2 and the second row by 1/4. And that should give us 1.
Yeah, I was right. We have to achieve the identity matrix on the left side.
So 1/2 of 2 is 1. And 1/2 of 4 is 2. 1/4 of 4 is 1. So all of these will be 1. And then the last one is not going to change.
And so the matrix on the right hand side is the inverse, right?
So notice that here we have the multiplicative identity matrix I3.
Yes.
And this side represents the inverse of matrix A. 1, 1, 2, 1, 1, 1, 2, 3, 4.
That's cool.
Now to confirm that it's indeed the inverse,
we should, wait, let me guess. We should multiply the original matrix with the inverse matrix, and we should get the identity matrix, right? To check if everything is correct, right?
what we need to do is multiply matrix A by the inverse of A and show that it's equal to I3.
Very good.
So in other words, we need to take matrix A, which was 1, 2, negative 1, negative 2, 0, 1, 1, negative 1, 0, and multiply it by the inverse of that matrix, which is 1, 1, 2, 1, 1, 1, 2, 3, 4. And if this is the matrix of A, if we did it correctly, we should get this answer: 1, 0, 0, 0, 1, 0, 0, 0, 1. So let's find now if we did it correctly.
So we have to compute the separation. 1 times 1, it's 1. Then plus 2, plus minus 1, negative 1, and this is 1, right? Now we have 2 plus 2. Wait, hold on. Oh wait, I'm dumb. I mean, we still have the first row. Then we have 1 plus 1 plus 2 minus 3, and this is 0, right? Then we have 2 plus 2 minus 4, and this is 0. Now let's do for the second. So the first part is correct, and we have negative 2 plus 0 plus 2, and this is 0. Then we have negative 2 plus 0 plus 3, and this is 1. Then we have negative 2 plus 0 plus 4. Wait, negative 4 plus 0 plus 4, and this is 0. Alright? Then we have 1, 2, and then we have 2 minus 1, which is 1. Wait. Yes. And 0. And this should be 2 minus 1. Yeah, it's 1. So, yeah, it's correct.
So I'm going to put my answers in here. First, we need to take the first row and multiply it by the first column and add the products. So it's going to be 1 times 1. So we're multiplying these two first. and then it's going to be plus 2 times 1, that's these two, and then plus negative
2.
1 times 2. So 1 times 1 is 1, 2 times 1 is 2, negative 1 times 2 is negative 2. These two cancel, and so we get 1. So we have the first entry. Now, let's multiply row 1 by column 2. So it's going to be 1 times 1 plus 2 times 1 plus negative 1 times 3. So this is 1 plus 2 minus 3. 1 plus 2 is 3. 3 minus 3 is 0. Now let's try row 1 by column 3. So that's 1 times 2 plus 2 times 1 plus negative 1 times 4. So this is 2, 2 minus 4. 2 plus 2 is 4. 4 minus 4 is 0. Now let's move on to row 2. And let's multiply it by column 1. So it's going to be negative 2
That's basically how to calculate the inverse of a matrix.
1 plus 1 times 2.
That's interesting.
So this is negative 2 plus 0 plus 2. Negative 2 plus 2 is 0. Now let's take row 2 and multiply it by column 2. So it's going to be negative 2 times 1 plus 0 times 1 plus 1 times 3. So that's negative 2 plus 0 plus 3. Negative 2 plus 3 is 1.
What the hell?
Now let's multiply row 2 by column 3. So negative 2 times 2 plus 0 times 1 plus 1 times 4. So this is going to be negative 4 plus 0 plus 4, which adds up to 0. Now, row 3 times column 1. Let's try that. So it's going to be 1 times 1 plus negative 1 times 1 plus 0 times 2. So it's 1 minus 1 plus 0, which is going to be 0. Next is going to be row 3 and then column 2. So this takes some time. I mean, it's pretty laborious, but
yeah,
that's how you can confirm it. So it's going to be 1 times 1.
I totally agree with that statement.
Negative 1 times 1, and then 0 times 3. So this is 1 minus 1 plus 0, which is 0. And finally, the last one. It's going to be row 3 times column 3. So that's going to be 1 times 2 plus negative 1 times 1 plus 0 times 4. So it's 2 minus 1 plus 0. 2 minus 1 is 1. And so we do get the identity matrix. So that tells us that this is indeed the inverse of A. So now you know how to find the inverse of a 3 by 3 matrix. Thanks for watching.
So, also let's define the, after we define all of this, let's also define the matrix T, and we define the we also define this. So that means so only square matrix can be inverted, like we saw in the book, on this book, right? In the MML book. So if the inverse exists, it's invertible, and if it exists, it is unique. So only square matrix can have inverse, right? So can non-square matrices be invertible? No, they cannot. Easy. So we have this is basically it. Like, we should use the Gaussian elimination. Then we have to use, wait, oh wow. Then we have to use we have to convert it to a row echelon form, and then we have to transform the first matrix into a identity matrix, and then we find the inverse. So we now know how to do that, right? I still have to practice on the Gaussian elimination, and I still have to, I just have to implement this algorithm. Okay. So it's actually pretty easy. So let's do something extreme. Do you know what I'm about to do? I'm about to delete all of this. I will keep this part right here, but the rest will be deleted. That's interesting. So, in the meantime, let's try to implement this algorithm, right? So this looks easy. Yeah. Just trying to get so we have this part. So let's focus this. I keep getting distracted for some reason, so we have to subtract this. So what do we need to start? We have to start the pivot, right? So let's try to find the pivot, right? Probably. So we have the matrix type, and then we have to specify the row, I guess. And I created a Python script a while ago, but I'm gonna recreate it anyway. So to do that, it's actually pretty simple. Like, we have switch columns, switch rows, we have the determinant, and we have right here we can calculate the pivot of this matrix, and then we have the size type, and then we specify the row, right? Also, I think we should include std_int.h. So what if, wait, let's see. I can just return -1, but I would rather use this, right? I can just return -1, but I'm just gonna return size max. So, the fuck is happening? Stupid fucking process. So right now what we have, so if row is 0, we return max size or size max. Yeah, wait, what's the actual? Wow, we return this. So let's define this. This should be sides max. Okay. So we will return met and pose, right? So now let's iterate this. So we're gonna do a simple for loop, right? We have I equals to 0. Then we have I plus plus. Wait, what the fuck am I doing? Then we have probably matrix dot columns. I mean also this should we can just return 0. So if we get, let's define the pivot. Then I'm just gonna wait, let me try with this approach. So we get matrix, and we have a row and the pivot, right? Is equal to 0. Not sure if that will work, but let's try it. Actually, this should be 1. Right? Yeah, this should be 1. So let's see if that's actually true. I don't know, let's try to find the pivot of this. So let's try to printf %u of this. So we have pivot of a, and I'll write this uppercase, then we pass this, and we also need to specify the row. Let's try this. It is 3. 1, 2, 3. Oh, that's true. Let's try with 1. It should be 2. Yes. Yeah, that was pretty simple. So yeah. So now we have this serial function. Let's do this. We definitely need the pivot, right? So before we switch, should actually get hold on. Bro, why does this fucking glitch? Oh my god, this is so annoying. So first we have to compute the operations, then we have to switch, right? So let's do this, I guess. So let me just get rid of this. It's only confusing me. Actually, let's get rid of all of this. Okay. Now, what do we have? So we have we actually have to start from 2, right? Now what we have to do is we should get we should multiply, we should actually subtract, right? So what do we have to do? We have to evaluate this matrix, right? Now we have the fucking matrix. Then we have I and J. And this should be okay. So this matrix I and J wait, no, we actually need another for loop here. Yeah, definitely need another one. Then we have to start from h plus 1, right? Then we have to define the value, right? I mean, not exactly. You don't have to define anything here. So we have this minus this matrix H and then J times this and pivot of this matrix, and the row should be I guess. Not sure. I'm not sure. But let's try with this approach. It definitely it's not gonna work, but I just wanna try what how it puts. So let's just compile and run this. That's something. That's nothing. I don't know. It shouldn't be like that. Why is it like that? What the hell? Let me try with this matrix. So let me rewrite this. So we have 1 2 1 0 4 2. Then we have, let me finish the animation. I'm gonna just 1262. Then we have 2088. Then we have 2194. Now let's try to bring this. So what's going to happen? What? That's not correct. It should be -4, but for some reason it's not -4. I don't understand the fuck is going on. So we take the value, right? Minus the shit. What happened here? Why is the spacing so fucking weird? I really don't understand, like... It should be 2, right? It should be 0. Nothing changes. Nothing fucking changes. What the fuck? You should iterate for each fucking column. So we have the fucking I and J. How the fuck are you? Wait, I think we have to store the pivot outside. And this is not a good thing actually. So we have to store the pivot outside. So let's create a size t pivot and we'll pass this. I call it P. Now we should pass P. Oh, now we get the right result. Zero, 2, 2, 0. Then we have 0, 0, 0, 4. Well, we have 1, 0, 4, 6. What the fuck? Let's print something here. Okay. Sure, just print I. This shit doesn't make any sense. Try to bring this side, this up. understand why it doesn't match. Fuck that shit, honestly. Let's print the people. What the fuck? Why doesn't it work? Like, I'm literally. Wait. It should be. It should be like that, probably. No. Fucking not. Oh wait, I mean here. What the fuck is he doing? So let's try to. Let's try to copy this matrix. So what we have right now, we have 1, 0, 4, 2, 1, 2, 6, 2, 2, 0, 8, 8, 2, 1, 9, 4. Here we are. So the first step is to do this. So the row 2 minus row 1. Wait. Okay, we get there. This is the second row, right? Minus row 1. And this is multiplied by 1. Then on the next step, we do the same process. So we do R3 minus R1 multiplied by 2, right? Because that's the fucking pivot, right? Then we have R4, and it's the fucking same process. And for some reason this doesn't work. So R2 minus R1. So we should always keep this, right? Multiplied by the pivot, right? That's the fucking pivot. I don't get it. I really don't get it. Let me just... God fucking damn it, don't fucking copy. What the fuck? Wait. Oh. Whoops. For some reason this is 1046, but it's not correct. It's actually 0004. So 1 minus 1, 2 minus 0. Okay. 2 minus 2 times 1. Wait. This should be I, probably. Wait, wait a second. Wait a minute. This should be actually multiplied. Let me just get rid of this temporarily. we should calculate the pivot. Should get the pivot of the current. Bro. I'm not sure, but let's try. And it doesn't work. Fuck off. Stupid fucking. So we have this fucking thing right here, right? We have the current thing, right? That's the fucking pivot of this. Right? Oh wait. Wait. Oh wait. No. Okay. That's. So we have the first matrix, right? It is age. I mean the first row. It is age. This is age. Right? And this should be multiplied by this. So why isn't working? Why it's not working then? What the fuck is your issue? What the fuck is your fucking issue then? Why are you not working? I'm gonna. So we have this, right? 1 minus 1, 2 minus 0. Okay. And we have 2 minus 2. Let's do this in order. So we have. Let me place this in order so I don't get confused. And let me print this fucking value. Wait, what the fuck? Wait, huh? What do you mean? Wait. Okay. Let me print everything. So the pivot is 1, right? Then the pivot is 2. That's correct. Wait, no. This isn't correct. Oh my fucking god. Actually, this is the actual pivot. So we can just put P. This cannot be 0. How the fuck is this 0? Wait, I think I have to start the volume. Yeah, I have to start the volume. Call it X. Don't care. I fucking need to start the value because it's actually changing. That's probably why I have this issue. So this should be X. Let's try again. And the numbers are more reasonable. And then we have it. We have it! Yes! Okay, we finally have the right result. The only issue is we had to store the value because of the matrix that is constantly changing. That makes sense. So let me just put that here so we can. Alright. So we can just get rid of this and print the matrix here, probably. Or maybe let's print that here for now. Let's compile this and run. So we have this, right? Then we have this. Okay. 004, and then we have 0110. Right? That's true. We can check it. That's true. Okay, the first step is almost complete. And Jesus, that took me a while. We still have 50 minutes, right? But at least we finally completed the first part. That's cool. That's cool. Now let's proceed with the switch part. So what we have to do right now, we have to switch this. And we should stop. God fucking damn it. So after we iterate this, we now have to sort. Am I right? Yeah, what we have to do, we have to keep track of the pivot, and then we have to resort the array based on the pivot. That's what is doing this. That's what they are doing here. At least we know how it works. At least we know how to calculate this. So what we have, like, we have to apply the Gaussian elimination, right? And after we did that, we should turn the upper right corner to 0. So the row echelon form is completely skipped. So then we have to do the same thing for the we have to shift vertically, right? And get the 0. Then we have to go on the middle one and then apply these two operations. And that's how we find the determinant. I mean the inverse of a matrix. Yeah. That's basically how it works. Then we learned how to solve linear equations and everything like that. So that's basically the first part, right? That's pretty much how it works. The next topic is vector spaces. Also, before we leave, can we check So let's try to watch this. I'm gonna try to rewatch this probably. And then I will watch this.
As you can probably tell by now, the bulk of this series is on understanding matrix and vector operations through that more visual lens of linear transformations. This video is no exception, describing the concepts of inverse matrices, column space, rank, and null space through that lens. A forewarning though, I'm not going to talk about the methods for actually through that lens. A forewarning though, I'm not going to talk about the methods for actually computing these things, and some would argue that that's pretty important. There are a lot of very good resources for learning those methods outside.
Wait, hold on, let me just...
Inside this series, keywords Gaussian elimination and row echelon form. I think most of the value that
Oh yeah, we just did it.
I actually have to add here is on the intuition half. Plus, in practice, we usually get software to compute this stuff for us anyway. First, a few words on the usefulness of linear algebra. By now you already have a hint for how it's used in describing the manipulation of space, which is useful for things like computer graphics and robotics. But one of the main reasons that linear algebra is more broadly applicable and required for just about any technical discipline is that it lets us solve certain systems of equations. When I say system of equations, I mean you have a list of variables, things you don't know, and a list of equations relating them. In a lot of situations, those equations can get very complicated. But, if you're lucky, they might take on a certain special form. Within each equation, the only thing happening to each variable is that it's scaled by some constant. And the only thing happening to each of those scaled variables is that they're added to each other. So no exponents or fancy functions or multiplying two variables together, things like that. The typical way to organize this sort of special system of equations is to throw all the variables on the left and put any lingering constants on the right. It's also nice to vertically line up the common variables, and to do that you might need to throw in some zero coefficients whenever the variable doesn't show up in one of the equations. This is called a linear system of equations. You might notice that this looks a lot like matrix vector multiplication. In fact, you can package all of the equations together into a single vector equation where you have the matrix containing all of the constant coefficients and a vector containing all of the variables, and their matrix vector product equals some different constant vector. Let's name that constant matrix A, denote the vector holding the variables with a bold-faced X, and call the constant vector on the right-hand side V. This is more than just a notational trick to get our system of equations written on one line. It sheds light on a pretty cool geometric interpretation for the problem. The matrix A corresponds with some linear transformation, so solving AX equals V means we're looking for a vector X, which, after applying the transformation, lands on V. Think about what's happening here for a moment. You can hold in your head this really complicated idea of multiple variables all intermingling with each other just by thinking about squishing and morphing space and trying to figure out which vector lands on another. Cool, right? To start simple, let's say you have a system with two equations and two unknowns. This means the matrix A is a 2 by 2 matrix, and V and X are each two-dimensional vectors. Now, how we think about the solutions to this equation depends on whether the transformation associated with A squishes all of space into a lower dimension, like a line or a point, or if it leaves everything spanning the full 2 dimensions where it started. In the language of the last video, we subdivide into the cases where A has 0 determinant and the case where A has non-zero determinant. Let's start with the most likely case, where the determinant is non-zero, meaning space does not get squished into a zero area region. In this case, there will always be one and only one vector that lands on V, and you can find it by playing the transformation in reverse. Following where V goes as we rewind the tape like this, you'll find the vector X such that A times X equals V. When you play the transformation in reverse, it actually corresponds to a separate linear transformation, commonly called the inverse of A, denoted A to the negative 1. For example, if A was a counterclockwise rotation by 90 degrees, then the inverse of A would be a clockwise rotation by 90 degrees. If A was a rightward shear that pushes j hat 1 unit to the right, the inverse of A would be a leftward shear that pushes j hat 1 unit to the left. In general, A inverse is the unique transformation with the property that if you first apply A, then follow it with the transformation A inverse, you end up back where you started. Applying one transformation after another is captured algebraically with matrix multiplication. So the core property of this transformation A inverse is that A inverse times A equals the matrix that corresponds to doing nothing. The transformation that does nothing is called the identity transformation. It leaves I hat and j hat each where they are, unmoved, so its columns are 1, 0 and 0, 1. Once you find this inverse, which in practice you'd do with a computer, you can solve your equation by multiplying this inverse matrix by V. And again, what this means geometrically is that you're playing the transformation in reverse and following V. This non-zero determinant case, which for a random choice of matrix is by far the most likely one, corresponds with the idea that if you have two unknowns and two equations, it's almost certainly the case that there's a single unique solution. This idea also makes sense in higher dimensions, when the number of equations equals the number of unknowns. Again, the system of equations can be translated to the geometric interpretation where you have some transformation A and some vector V, and you're looking for the vector X that lands on V. As long as the transformation A doesn't squish all of space into a lower dimension, meaning its determinant is non-zero, there will be an inverse transformation, A inverse, with the property that if you first do A, then you do A inverse, it's the same as doing nothing. And to solve your equation, you just have to multiply that reverse transformation matrix by the vector V. But when the determinant is 0, and the transformation associated with the system of equations squishes space into a smaller dimension, there is no inverse. You cannot unsquish a line to turn it into a plane. At least that's not something that a function can do. That would require transforming each individual vector into a whole line full of vectors. But functions can only take a single input to a single output. Similarly, for 3 equations and 3 unknowns, there will be no inverse if the corresponding transformation squishes 3D space onto the plane, or even if it squishes it onto a line or a point. those all correspond to a determinant of 0, since any region is squished into something with 0 volume. It's still possible that a solution exists even when there is no inverse. It's just that when your transformation squishes space onto, say, a line, you have to be lucky enough that the vector v lives somewhere on that line. You might notice that some of these zero determinant cases feel a lot more restrictive than others. Given a 3x3 matrix, for example, it seems a lot harder for a solution to exist when it squishes space onto a line compared to when it squishes things onto a plane, even though both of those are zero determinant. We have some language that's a bit more specific than just saying zero determinant. When the output of a transformation is a line, meaning it's one-dimensional, we say the transformation has a rank of 1. If all the vectors land on some two-dimensional plane, we say the transformation has a rank of 2. So the word rank means the number of dimensions in the output of a transformation. For instance, in the case of 2x2 matrices, rank 2 is the best that it can be. It means the basis vectors continue to span the full 2 dimensions of space and the determinant is non-zero. But for 3x3 matrices, rank 2 means that we've collapsed, but not as much as they would have collapsed for a rank 1 situation. If a 3D transformation has a non-zero determinant and its output fills all of 3D space, it has a rank of 3. This set of all possible outputs for your matrix, whether it's a line, a plane, 3D space, whatever, is called the column space of your matrix. You can probably guess where that name comes from. The columns of your matrix tell you where the basis vectors land. And the span of those transformed basis vectors gives you all possible outputs. In other words, the column space is the span of the columns of your matrix. So a more precise definition of rank would be that it's the number of dimensions in the column space.
Wait.
Vectors land. Name comes from. The columns of your matrix tell you where the basis vectors land. And the span of those transformed basis vectors gives you all possible outputs. In other words, the column space is the span of the columns of your matrix. So a more precise definition of rank would be that it's the number of dimensions in the column space. When this rank is as high as it can be, meaning it equals the number of columns, we call the matrix full rank. Notice, the zero vector will always be included in the column space, since linear transformations must keep the origin fixed in place. For a full rank transformation, the only vector that lands at the origin is the zero vector itself. But for matrices that aren't full rank, which squish to a smaller dimension, you can have a whole bunch of vectors land on 0. If a 2D transformation squishes space onto a line, for example, there is a separate line in a different direction full of vectors that get squished onto the origin. If a 3D transformation squishes space onto a plane, there's also a full line of vectors that land on the origin. If a 3D transformation squishes all of space onto a line, then there's a whole plane full of vectors that land on the origin. This set of vectors that lands on the origin is called the null space, or the kernel of your matrix. It's the space of all vectors that become null, in the sense that they land on the zero vector. In terms of the linear system of equations, when v happens to be the zero vector, the null space gives you all of the possible solutions to the equation. So that's a very high-level overview of how to think about linear systems of equations geometrically. Each system has some kind of linear transformation associated with it, and when that transformation has an inverse, you can use that inverse to solve your system. Otherwise, the idea of column space lets us understand when a solution even exists, and the idea of a null space helps us to understand what the set of all possible solutions can look like. Again, there's a lot that I haven't covered here, most notably how to compute these things. I also had to limit my scope to examples where the number of equations equals the number of unknowns. But the goal here is not to try to teach everything. It's that you come away with a strong intuition for inverse matrices, column space, and null space, and that those intuitions make any future learning that you do more fruitful. Next video, by popular request, will be a brief footnote about non-square matrices. Then after that, I'm going to give you my take on dot products, and something pretty cool that happens when you view them under the light of linear transformations. See you then. Hey everyone, I've got another quick footnote for you between chapters today. When I've talked about linear transformations so far, I've only really talked about transformations from 2D vectors to other 2D vectors, represented with 2x2 matrices, or from 3D vectors to other 3D vectors, represented with 3x3 matrices. But several commenters have asked about non-square matrices, so I thought I'd take a moment to just show what those mean geometrically. By now in the series, you actually have most of the background you need to start pondering a question like this on your own, but I'll start talking through it just to give a little mental momentum. It's perfectly reasonable to talk about transformations between dimensions, such as one that takes 2D vectors to 3D vectors. Again, what makes one of these linear is that grid lines remain parallel and evenly spaced, and that the origin maps to the origin. What I have pictured here is the input space on the left, which is just 2D space, and the output of the transformation shown on the right. The reason I'm not showing the inputs move over to the outputs like I usually do is not just animation laziness. It's worth emphasizing that 2D vector inputs are very different animals from these 3D vector outputs, living in a completely separate, unconnected space. Encoding one of these transformations with a matrix is really just the same thing as what we've done before. You look at where each basis vector lands and write the coordinates of the landing spots as the columns of a matrix. For example, what you're looking at here is an output of a transformation that takes I hat to the coordinates 2, -1, -2, and j hat to the coordinates 0, 1, 1. Notice, this means the matrix encoding our transformation has 3 rows and 2 columns, which, to use standard terminology, makes it a 3x2 matrix. In the language of last video, the column space of this matrix, the place where all the vectors land, is a 2D plane slicing through the origin of 3D space. But the matrix is still full rank, since the number of dimensions in this column space is the same as the number of dimensions of the input space. So if you see a 3x2 matrix out in the wild, you can know that it has the geometric interpretation of mapping 2 dimensions to 3 dimensions, since the 2 columns indicate that the input space has 2 basis vectors, and the 3 rows indicate that the landing spots for each of those basis vectors is described with 3 separate coordinates. Likewise, if you see a 2x3 matrix with 2 rows and 3 columns, what do you think that means? Well, a 2x3 is described with 3 separate coordinates. Likewise, if you see a 2x3 matrix with 2 rows and 3 columns, what do you think that means?
Probably like there are 3D vectors in a 2D space.
Well, the 3 columns indicate that you're starting in a space that has 3 basis vectors, so we're starting in 3 dimensions. And the 2 rows indicate that the landing spot for each of those 3 basis vectors is described with only 2 coordinates, so they must be landing in 2 dimensions. So it's a transformation from 3D space onto the 2D plane. A transformation that should feel very uncomfortable if you imagine going through it. You could also have a transformation from 2 dimensions to 1 dimension. One-dimensional space is really just the number line, so a transformation like this takes in 2D vectors and spits out numbers. Thinking about grid lines remaining parallel and evenly spaced is a little bit messy due to all of the squishification happening here. So in this case, the visual understanding for what linearity means is that if you have a line of evenly spaced dots, it would remain evenly spaced once they're mapped onto the number line. One of these transformations is encoded with a 1x2 matrix, each of whose 2 columns has just a single entry. The 2 columns represent where the basis vectors land, and each one of those columns requires just one number, the number that that basis vector landed on. This is actually a surprisingly meaningful type of transformation, with close ties to the dot product, and I'll be talking about that next video. Until then, I encourage you to play around with this idea on your own, contemplating the meanings of things like matrix multiplication and linear systems of equations in the context of transformations between different dimensions. Have fun!
So I think for today it is enough. I was streaming for over 6 hours, so I will see you later. We probably later if nothing else unexpected happens with the OpenGL learning.